Great pleasure for me to present Myung Soo. Myung Soo is a very long, great friend that I have for many years, since I think we were young professors. We collaborated a lot with many papers and many exchange researchers, including today. We have Kyoyon here. Today, Myung Soo is going to talk about some acceleration or improving geometric algorithm for freeform surfaces using toroidal patches. I have to admit that I'm a little bit involved in that research as well. And Myung Soo, you have the podium.
Okay, thank you very much, Gershon, for a nice introduction. The title of my talk is Accelerating Geometric Algorithms, but I would like to update the title a bit, Improving, because I realized that we actually not doing acceleration of the algorithm, but we also do some of the improvement in different aspects. So the improving performance, not only speed and the space reduction, in the last couple of years, we have done much work on stability improvement and then improving the precision of the computation. Okay, so, well, at the core of this improvement is special data structures for freeform geometric models. Data structure is the main thing for geometric algorithms for discrete objects. This whole book is about the spatial data structure. But in CHD and for the representation or processing of freeform geometric models, we have not really done much on the data structures. Even in these two famous standard textbooks for CHD, we don't have any chapter or section on data structure. Even in this handbook that has more than 30 chapters, we have no chapter on spatial data structure. The only exception is in the Professor Horsak's CHD textbook. In chapter 12 on intersection of curves and surfaces, there is a section on subdivision method. There is a simple quad tree structure. The caption of the video really tells you that the quad tree data structure. When you subdivide a rectangular surface patch into smaller pieces, we generate the child nodes like this. When it subdivide the triangular patches, we also generate the 4 child node. We can do the uniform subdivision again and again, and then we will generate the balanced tree. And when you do non-uniform subdivision, you will generate regular quad tree like this. So we have this tree structure in CHD, but in the past, this concept was conceptual. You know, this quad tree is conceptual. On the fly, we generated these things, but by generating this structure in a pre-processing step and then storing this tree in the memory, we have data structure. And then conventionally, in CHD, we consider the convex hull of control points the main convex bounding volume for the surface, or sometimes AABB was used. But we can have another large variety of bounding volumes for the nodes around the root node, or for leaf nodes, we can use some other things. So in our recent research result, we used osculating toroidal patches for those leaf nodes. That's the basic difference from the previous approaches. So before we go to more technical details, I'll try to present our past experience in the about several years ago in improving the speed and this reducing storage size for geometry computation or spatial data structure. This is a result in 2015 for detecting the collision between deforming tree branches. So you can see that we represent tree branches as a B-spline curve with a certain thickness. So cylindrical shapes are good for bounding these branch shapes. So we have certain hierarchy of cylinder-like bounding volumes for accelerating the collision detection for this dynamically deforming geometric model. When you try to do the same thing using triangular mesh models, dynamic update for bounding volume hierarchy will be extremely difficult and time-consuming, but using this spline representation of this geometric model, we can do much better. Here, we have B-spline surfaces under deformation. And then we use tetrahedral-based bounding volume for efficient bounding of local shapes of this geometry model. Okay, this is pre-recording. This is not the real-time computation because there are too many geometry models there. So here, each frame took about 20 seconds, and we used the Kunz bounding volume. And I will explain Kunz bounding volume shortly. So this is another Kunz for static model. So on this one, each frame took about 1 second in pre-recording. This is the red line shows the shortest distance from a airplane to the object in the environment. This one is, real-time screen capture. This one is application of bounding volume to Hausdorff distance computation. This screen capture, almost interactive real-time computation. Now we have two different objects. So the Hausdorff distance computation can be done much faster. And then we have application to planar geometry models, sorry. So we have very, very complex planar region, and then we have the construction of the medial axis in 35 milliseconds. This is the result 2016. We may do slightly faster using new CPUs and GPUs, but still these things can be done with less than 1 second. So we generated a very, very, very complex geometric model intentionally to introduce all these fractal-like structures. And then medial axis can be constructed within 224 milliseconds using bounding volume hierarchy for planar geometry models. This is screen capture of a medial axis computation for deformable freeform models. So this one actually shows you the performance, but we don't go to too much details for planar geometric ones. Okay, so this one actually shows some idea. So we wanted to develop the bounding volume hierarchy for performance improvement for geometric algorithm for freeform surfaces. Conventionally, bounding volume hierarchy was used for polygonal models. Myung and Dinesh Manoj has done a lot of work for BVH-based research for real-time collision detection and the distance computation and rendering. Public library with open source to general public. And then our motivation why we moved to bounding volume research was based on the result published in SIGGRAPH 2009 by Korean professor at Ewha Women's University. His name is Young Kim. He's not young anymore, but his name is Young Kim, who did the postdoc work together with under Dinesh Manocha many years ago. And then he presented interactive speed Hausdorff distance computation. And at that time, Gershon and myself was doing Israel-Korea binational research project. Hausdorff distance computation was one of the most important topic in that project. And then we realized that their algorithm is much faster than ours. So this is Gershon's comment, too good to be true. So we decided to move in this direction. And there is another Korean professor at KAIST who did a PhD from Dinesh Manocha. He is an expert in dynamic reconstruction for deformable polygonal meshes. I had some discussion with the Professor Yoon at KAIST, and then we realized that spline models has a lot of advantage in dynamic reconstruction of this spatial data structure compared with the bounding volume hierarchy for polygonal meshes because of beautiful spline structures and equations and then all these extra structures and geometry available. So we decided to continue this research. And then I'll show you some of our very recent results published last year in Eurographics. On the left, the result was done by polygonal approximation. On the right, we do direct computation of minimum distance among torus using geometric facts that the distance between torus can be computed by measuring the distance between their center circles. So obviously, the one on the right is faster and more accurate. This is another example. The dynamic simulation was done in a different software, public software called ODE. And then when you tried to simulate with the polygonal approximation, the software didn't really work because of certain, memory problem or something like that. But basically, we are handling it, circles here, so we could actually generate this simulation. Okay, so I'll then review some of the bounding volumes used in graphics and the geometric modeling and the geometric algorithms. And the conventional bounding volume hierarchy tree used the spheres and AABB and OBB and the KDOB. OBB was developed by UNC Gamma Group, Myung and Dinesh Manocha, and they replaced OBB to something else. These days, PQP library use LSS, RSS, that's line-based bounding volume, a rectangle-based bounding volume. And then they also suggested the shell for bounding volume for spline surfaces. But we replaced the shell tree to something based on osculating tori. In the case of GPU implementation, because of the rigidity of GPU implementation, and Sarah McMahon at UC Berkeley used only AABB for GPU implementation. But for CPU implementation, we can use more flexible bounding volume. Young Kim at Ewha Umunje University developed Hausdorff distance computation based on PQP library. So he used the LSS or RSS bounding volume. And then the Young Kim was a former postdoc at Technion working with the Gershon Elbow for 2 years. In his PhD thesis in my research group, he developed the Kunz bounding volume. 2011, he applied this bounding volume for collision detection and the minimum distance computation. In 2012, he developed Hausdorff distance computation for nerves using about the same bounding volume. And then he actually handled almost identical, the Hausdorff distance between almost identical surfaces. That was considered to be extremely difficult, but he handled that case. And we also developed many arc trees for planar geometric models, but I wouldn't have enough time to actually discuss about this topic. Okay, so this is a bounding volume hierarchy in the textbook of real-time rendering. So here, the bounding volumes, a hierarchy of spheres. And in that textbook, the author shows sphere, AABB, OBB, and KDOB in the planar view. And then OBB was replaced by something else here. So sphere, and then the line-based sweeping a sphere along line or sweeping a in our own research, we use these bounding volumes a lot. Another one was spherical shell. Spherical shell has 2 spheres, outside, inside, with the same center. And then the lateral part is bounded by cone. And this one is relatively okay for bounding convex surfaces, but the concave part is a bit rather difficult to actually bound with using a spherical shell. So we suggest torus-based bounding volumes like this for a positive curvature, for negative curvature, for zero curvature, zero Gaussian curvature. This is a cylinder-based bounding volume. And we also suggest tetrahedron-based bounding volume, quadrangle-based bounding volumes. So we have many animals in the zoo of bounding volumes. Okay, I will give you just some rough idea how tetrahedra-based or quadrangle-based bounding volumes behave. So we have rectangular surface patch, and then the tetrahedra or quad-based bounding volume has roughly this kind of shape. So, well, the bounding is not really that tight, but when you subdivide, we have a better approximation with quadratic convergence. So the thickness is reduced 4 times. When you divide once more, we will get the better and better approximation. But the this error estimation between original surface or tetrahedra or quad is based on mathematical formula, and there are much of overestimation. You can actually see some more of that effect here. So from this big spline surface, we took this small patch, and then using 4 corners of this patch, we generate the tetrahedra, and somehow we estimate that the error between this tetrahedra and original surface by mathematical equation. Somehow the estimation was too large, so we have a very thick one. And then these 4 corners are not in the same plane. By moving these points to some mid plane, we have quadrangle in the same plane. So thickness was a bit reduced, but these two are just about the same. Well, this is not really that tight, but the good point is it's extremely easy and fast to construct these two things. So when you deal with the deformable surface, tetrahedra-based or quadrangle-based bounding volume is the method of choice. But when the surface is static, we better to use rectangles as the basic shape, and then we have to measure the deviation from original surface to this rectangle more tightly, and then we have much better approximation there. But the construction of rectangle-based bounding volume is more time-consuming, but it's okay because we are dealing with the static object. I'll show you another figure without having the surface patch. So we have tetrahedral and then the thickness. Oh, the thickness is a bit bad, but it's okay because we can generate these bounding volumes much faster. And then basically we have quadratic conversion. So when you subdivide and subdivide and subdivide, we will have approximation of required accuracy. But for static model, we have to use this one, because in static model, we do all this computation in pre-processing, so we don't really care about how much time we actually take in the construction of special data structure. Okay, moving to the leaf node. When you have a surface and subdivide and subdivide and subdivide, and at the end we have very small surface patch, and then at the center point of the surface patch, we compute the curvature, so principal curvatures in this direction and in this direction. So we have osculating torus trimmed according to the shape of the surface patch. So because of the different direction of parameter direction and principal direction, oscillating torus may have a different shape like that, but we can actually trim this part and that part. And then we can make a trimmed osculating torus and the original small surface patch having about the same position and about the same normal direction at their corresponding perimeter locations. You can do that for the majority of surface parts except non-degenerate, non-regular points. At non-regular points, you cannot really do that. So we will come back to this issue shortly. Okay, so I'll give you just some rough idea what is the advantage of these spline-based bounding volumes. So I wouldn't really go to too much detail. Myung Kim developed the Kunz bounding volume. So for comparison purpose, we triangulated Utah teapot into many triangles. As a triangle soup, we put this data, a set of triangles to PQP library. And then this is the result of bounding volume generation from the public library. So because we don't have connectivity information, because it's the input was just a triangle soups. There was some bounding volume generated, but there is no structure because the parameterization was lost. And then another problem was the shape was quite irregular. So in the around the polar points, approximation is not really that good. There are too much cluster of these rectangle-based bounding volumes. But in the Kunz BVH, Kunz surface actually inherits the parameterization of the original surface. So we actually preserve the parameterization. In the polar points, the quadrangle shape looks almost like a triangular. So we have a better approximation to the polar part. In the majority of freeform geometric models, especially in the case of surface of revolution or solid of revolution, we have these polar points here and there. This is very important to represent polar points in a nice way. Okay, so, well, we have advantage. Sorry, there is a phone call. So we have quadrangle based or even tetrahedral based bounding volumes, and there are some advantages. Conspect is based on a boundary of a surface. Using boundary information, we generate a surface. So when you have Utah T part, we approximate this part using Kunz surface generated by only boundary information. So this is approximation within error bound of 10 to the minus second, 10 to the minus third, 10 to the minus fourth, 10 to the minus fifth. It's have a cubic approximation order, but in practice, when you increase approximation error 10 times, when you divide a certain patch into two pieces along U and V direction, we will generate 4 times more surface patches. And then the cubic approximation order means that the approximation error will be reduced 8 times. But even if we actually increase precision 10 times, it does not really increase 4 times. So practically maybe more than cubic. And then I didn't really give much details, but skipping the details of bounding volume hierarchy for Kunz, this is the data size for bounding volume. And then this is the data size for triangular approximation. So in this precision, degree reduction is more than 1,000 times. Here, not really 1,000 times, but we have other models. So this is more than 1,000 times. In this model, approximately 1,000 times. Oh, okay, so this is just give you some idea. When you use some specialized data structure for spline models, you can actually reduce the storage size for geometry model. And then the acceleration of the algorithm is another different issue. So I wouldn't go too much details about this technique because we have replaced the Kunz bounding volume hierarchy to something else. So I'll give some more technical details about the hybrid bounding volume hierarchy using osculating toroidal patches. That means hybrid means we use toroidal patches only for lip. And in the internal loss, we use different bounding volume, either tetrahedral based, quad based, or rectangle based, depending on its different geometry computations we need to actually support. So we will consider surface intersection. Well, 20 years ago, Gershon suggested to my former student, PhD student, her, to intersect two almost identical cylinders. So we start with the 2 cylinders making their axis having angle 10 degree. So these 2 cylinders are definitely different cylinder. And then we make their axis make angle 1 degree and 0.1 degree and 0.3 0.01 degree. And then we realized that in these large angles, the two cylinders visually look different. So they can actually preserve X junction. But when they, sorry about that, when the angle becomes smaller and smaller, they become almost identical surface. So at some point, the X junction was missing. So originally, we started with the one cylinder and rotated about the angle. So in this rotation angle is common to two cylinders. So the point at this rotation angle should appear in each intersection curve. But in this part, because of almost tangential interaction, we lost X junction. But using toroidal patches in all these lymph nodes, we have improved this. Oh, sorry about that. The X junction to there. We use exactly the same data. The rotation axis was just changed to a different direction. And we changed it, the angle to smaller and smaller and smaller. Because of many oscillating toroidal patches here and there, we could actually measure the distance from one surface point to the other surface quite accurately. The yellow region means the surface points within a small distance from the other surface. Distance 10 to the minus 8, a very small distance. So in the case of cylinders, they're almost like torus with a very large radius. But in the regular surface, we can actually apply the same technique. So the rotation axis over there, and we rotate, and then we replace all this computation with this, surfaces using oscillating toroidal patches, lymph nodes, and then we could actually compute intersection as a region because they are almost identical surfaces. So the intersection curve should be something like a surface patch like that. So X junction, our X junction may be somewhere around there, but we have much richer structure there. And then quite recently, we moved to surface Serpent section. This is a PhD work for PhD. This work should be part of my students' PhD thesis. So here we have a self-intersecting surface like that. This corner corresponds to the parameter here. This guy corresponds to there. This is a self-intersection curve. This part appears as blue in the perimeter domain. And when you go to the other side, the self-intersecting seen from the other side will be red. So when you glue these two things together, we will get the self-intersection curve. So this part corresponds to the inner over there. So when you fold these two things together, this point will be the folding point over there. In the middle of this yellow curve, the surface actually intersect tangentially, but at this point, non-regular point, surface normal is dramatically change to all different directions over there. So it's almost impossible. This is impossible to approximate the neighborhood of this mitre point using torus. So in fact, when you have a very tiny small ball there, the inverse map will correspond to a certain region in the perimeter domain. So we can actually compute, Kyuhyun Hong actually computed the exact location of this mitre point using symbolic and numerical computation. So this point can be detected, but the problem is the intersection curve around this mitre point is extremely difficult to construct reliably. even if we use toroidal patch approximation, toroidal patches to be intersected will be almost identical. So tangential intersection. 2005, Gallego, Pavoni actually the self-intersection curve around that kind of mitre point using triangular approximation, and then they have realized the intersection curve is generated in a zigzag fashion because all these triangles around this navy will be almost identical flat. So the thing is, we realize that around this mitre point, intersection curve should look very much like a straight line. Around the singular points, intersection curve also has a kind of straight line shape. So around this area, it's very difficult to, well, reconstruct the solution curve. So we replaced that area by a region, and then the whole thing mapped to Euclidean space will become kind of epsilon ball, smaller than 10 to the minus fifth. So we consider this region as a very, very, very unstable region, but it's okay. This intersection curve should be mapped to a very tiny line segment over there. And it may be extended to the same intersection direction, almost like a straight line. And then we tried to intersect this local surface with the 3 parallel planes. If the plane intersects with this very short yellow line segment, each intersection with yellow segment will be mapped to 2 different locations into red and then blue part, because this one and this one will be glued together to the same location to the yellow curve in the Euclidean space. So in the perimeter domain, we have this intersection curve as a loop. By gluing these two, we will have a figure. When we move this one a bit upward, the loop will become a bit smaller. And then we have a smaller 8 figure. When we have tangential intersection with the line segment, we will have just 1 point up there. And then we move up, and then there will be no intersection. And then there is another example. Well, in this case, the surface looks very much like a saddle surface over there. So intersection with the plane with original surface generates this kind of intersection curve in the UV parameter domain. When you glue these two things together, we will have this curve and then this curve, meeting at one point in a yellow line segment over there. And then when the plane have tangential intersection at this tip of the very short yellow line segment, we will have this kind of situation, and then this will be tangential intersection there, and we move up. The intersection curve will have intersection over there, and then we have 2 different branches. So we have this and that branch, and then this one goes to there, and then this part goes to here. So we can actually deal with these non-regular points by representing, this non-regular point causing a lot of computational difficulty as a relatively large region in the perimeter space. Okay, so this is a kind of different representation, and then we did these things in the pre-processing stage and stored everything in the data structure. And then actually we used this fact in the further geometry computations. And then finally, I'll move to Hausdorff distance computation. We revised Hausdorff distance computation again in 2012. Young-Jun Kim actually developed Hausdorff distance computation between two almost identical objects. He translated the one model along X direction, Y direction, and Z direction, a very short distance, and then rotated in a small angle here and there, and then computed Hausdorff distance in a reasonable computation time, but the precision of approximation was not really that great. And then in this work, Son, in the master thesis of Son, Sang-hyun Son, he tried to compute Hausdorff distance between two almost identical surfaces. He applied a small translation along many different directions, and then a small rotation. So he generated 728 different position and orientation, and then computed Hausdorff distance up to approximation error 10 to the minus third. So this level is the same as Young-Jun Kim, and then 10 to the minus fourth. Young Kim's approximation error is somewhere between there, and then Sarah Mengmen's UC Berkeley also used the approximation error in this area. -3 and -4 is logarithmic. Well, actually, this one corresponds to 10 to the minus third, 10 to the minus fifth, 10 to the minus sixth. So accuracy is increasing. So higher accuracy, we have to spend more computing time for generating the bounding volume with the high approximation error. So the tree becomes much larger. So the computing time is increasing up to 70 milliseconds. And then starting from there, we cannot really continue this way all the way. So we switched to numerical computation and got much improved error of almost machine precision, adding just some more milliseconds. This is average computation time for all different configurations. And then this is a different model. And this is computing time up to this much, and then adding about the 10% more computation, we actually get the result, much more accurate result, almost to machine accuracy. This is a horse model. And this is more time consuming because the model is more complicated. And then this is Gershon's dog model. And there are many polar points here and there, much more complicated. So we have to spend much more computing time. But the switching from here to higher accuracy, we need only six milliseconds more. And then the approximation error is almost machine precision. And then our advantage is handling surface of revolution. In the case of surface of revolution, using the symmetry, we could compute the Hausdorff distance much faster. And this one, almost real time. And then we have other models like this. So 20, and then this is a bit more expensive, but it's okay. So in this case, we compared two almost identical models, but switching to quite a different models. So we generated deformable model of 1,000 frames. So we have 1,000 frames. So we have a purple model deforming to something else, dynamically changing to something else. And then we have a brown one deforming to something else. And these two have different shape and then the different position and orientation. So, well, in these cases, it's much faster to compute Hausdorff distance, but the model is changing. So the blue means model update for bounding volume hierarchy. And the red is computing time for Hausdorff distance. And then black here shows the Hausdorff distance. Sometimes the distance is approximately 30 times larger than the model size or something like that. So in this talk, I presented some techniques for improving the performance of geometric algorithm using hybrid bounding volume hierarchy, especially designed for freeform geometry models. Especially we used osculating toroidal patches trained in a nice way for approximating the surface patch in the lymph nodes. In the future work, we would like to extend the result to Voronoi diagonal construction. And also we wanted to apply this technique for computing integral properties for freeform geometric models. Okay. Okay, Toda Raba, thank you very much. This is the end of my talk, and I would like to answer to some questions.
감사합니다.